Let's look at three families of distributions: the normal, the logistic, and the Cauchy. These are families of distributions where each member is indexed by a particular set of parameter values. And I will pick one member from each of these three families so that they are as similar to each other visually as possible. Whenever we look at a bell-shaped distribution like one of these three, our attention naturally goes to that part of the distribution that encloses most of the area, the bell-shaped region, so to speak. And naturally so, because look, the tails, they blend into each other. But the amazing thing is that for such bell-shaped distributions, much of the personality actually rests in the tails. And as we travel farther and farther into the tails, we can see that these distributions are actually incredibly different from each other. Two of these distributions have an expected value of 2, the normal and the logistic. The Cauchy, the one in green, looks quite similar to the other two, but the crazy thing is that it doesn't have an expected value at all, and no amount of zooming is going to convince us of that fact. That is because the expected value is not a visual concept, it is a precise mathematical concept. Visuals are incredibly useful, they help us build intuition, but at the end of the day, it is the mathematics that tell us the full story. Starting with this section, we're going to become more mathematical. Math will be our microscope. It will allow us to see things that our eyes cannot see on their own. The Cauchy distribution, having no expected value, is our first example of exactly that. Let's briefly outline what we'll cover in this section. We will start by defining what the expected value of a random variable x is, and we will see that it is in all cases just a weighted average of the values that this random variable can take on times the point probability of each of those values. It is important to notice that the definition of the expected value has a contingency. In other words, if x is a continuous random variable, we will define the expected value of x to be the expression in A here. We will say that the expected value of x exists only if another expression, which I labeled here with B, is finite, or less than infinity, or convergent, or exists. Those are equivalent way of stating the same thing. And if x is discrete, we will define the expected value of this random variable x to be the expression that I labeled here with C, but only if this other expression, which I labeled here with D, is finite or convergent or exists. Later in this section, we'll be able to recognize B and D as being just the expected value of the absolute value of the random variable x. Notice that it is these conditions B and D that give the expected value its legitimacy. Those conditions must hold for an expected value to exist. And those conditions are also stronger in the sense that I've outlined here at the bottom, where I'm saying that if the expected value of the absolute value of x is finite or convergent, then the expected value of x is guaranteed to be finite or convergent. But it doesn't work the other way around. If the expected value of x is finite or convergent, that does not mean that the expected value of the absolute value of x is also finite or convergent. So theory seems to suggest that when we're presented with a random variable x, and let's say that x is continuous, we should start by evaluating the expression b and see if it is finite or exists, because we need that condition to hold for the expected value to even be defined. And then we would go to evaluating what the expected value of x is, the expression in A here. But nobody does that in practice. when we're given a random variable, we will directly estimate the expressions A or C without bothering to check for the conditions B and D. But there is a gap here, right? There's a gap between A and B, and there's a gap between C and D. And that gap is to be understood, because it is technically possible that we might estimate the expected value of a random variable to be 20, but then the corresponding condition B or D would not hold, which means that whatever we calculated for the expected value, 20 in this case, is not the expected value of this random variable. The expected value of this random variable is said to not exist. We will work on understanding this gap by looking at several examples. And I've split these into 3 categories by rows. In category 1, in row 1, we will cover the binomial and the uniform, 2 random variables that have a finite support in the case of binomial and a bounded support in the case of a continuous random variable. And we will see that in such cases, the expected value of x and the expected value of the absolute value of x are both guaranteed to be finite and exist. Before we even calculate anything, we're guaranteed that they will exist. In row 2, we will look at one-sided random variables, such as the geometric, exponential, and Pareto. And we will see that the expected value of x is not guaranteed to exist in this case. But if we do find that the expected value of x is finite or exists, then that automatically will imply that the expected value of the absolute value of x is also finite, exists, so we don't need to do the additional check to verify that the expected value of the absolute value of x is finite. And finally, in row 3, we will group all the other random variables. For these, essentially, the expected value of x is not guaranteed to be finite, and even if we work out the expected value of x to be finite, we would still need to go and additionally check that the expected value of the absolute value of x is also finite. And we'll look at 3 examples here. So that will be sort of part 1 of the video, and then in part 2 we will go to what is really the substance covered in Casella and Berger, and we will do so by trying to evaluate the expected value of a random variable y, where y is a deterministic function of another random variable x whose distribution we know, and we'll try to evaluate this expected value of the random variable y in 3 different ways. The first way, using the definition as is. This will require that we derive the distribution of the random variable y first, something we learned how to do in the previous section, and then use it in the definition to get the expected value of the random variable y. We will see that this is unnecessary if all we need is the expected value of the random variable y. In other words, if we didn't need to know the distribution of the random variable y, there was no need to derive it, because there's a more direct way for us to get the expected value of the random variable y if we know only the distribution of the random variable x and the fact that y is a deterministic function of the random variable x. This more direct way goes by the name of LOTUS, which stands for the law of the unconscious statistician. And you'll see that the name comes from the fact that you could have written that expression by mistake, where it looks like we accidentally put in the PDF or the PMF of the random variable x, whereas we should have perhaps put in the PMF or the PDF of the random variable g of x. But it turns out we don't have to, because all the randomness of the random variable y can be attributed to the randomness of the random variable x, and so LOTUS is just a formalization of that intuition. And it always applies. It's a very powerful tool. We'll use it again and again. In those rare circumstances when the random variable y happens to be a linear function of x, so not just any generic deterministic function of x, but a linear function of x, we will see that we can use the linear property of the expectation operator to get an even more direct answer. But this method in part 3 applies only for linear functions, only when y is a linear function of the random variable x. Okay, that's the plan. Let's get started. I want to start by explaining how the binomial distribution arises and look under the hood of the binomial distribution and see that all it does there really is a counting exercise. Then we'll show that the binomial PMF adds up to 1, and we'll get used to identifying the binomial distribution in the wild when it doesn't have the parameters that we'll get used to, the NP parameters. But perhaps if there's a binomial with parameters n-1 and p, we want to be able to recognize that in the wild. And then we'll derive the expected value of a random variable with the binomial NP distribution. The binomial family of distributions is indexed by a set of two parameters, n and p, where n stands for the number of trials and p for the probability of success on each of these n trials. Different values of these two parameters will refer to a different member of the binomial family of distributions. And every time we hear of a binomial, a certain story needs to come to mind, because a binomial arises only in the case of IID Bernoulli trials, where IID stands for independent and identically distributed. When you hear that X is a binomial NP distribution, you should think of X as standing for the number of tails in n IID tosses of a coin. And I've written the PMF of the binomial distribution here in orange. This PMF gives us the probability that our random variable X takes on any particular value, and we can evaluate that probability using this formula. Now let's have a quick look at where this formula comes from. Let's look at the particular example when n equals 4. In other words, we'll have X, a binomial random variable with parameters np, where n equals 4. In other words, the interpretation here is that X can stand for the number of tails, where a tail is a success, the number of tails out of 4 tosses of a coin. And these tosses are IID, or better said, the random variables that encode these tosses are IID. There are 16 outcomes in the original sample space of this experiment, and I've listed them all here. And I have grouped them by the corresponding value of X. So here, X would equal 0, because there are 0 tails and 4 heads. For each of these elementary outcomes, X would equal 1. For each of these 6 here, X would equal 2. For each of these 4 here, X would equal 3. And for this outcome TTTT, X would equal 4 tails. Notice that because we did not say anything about the value of P, in particular, we did not say that P equals 0.5. We did not say that the coin is unbiased. Because we didn't do that, we do not know how to relate, for example, the probability of that outcome, which would end up with 1t, and the probability of this outcome, which would have 2 t's. We cannot say that those two outcomes would have the same probability. If p were equal to 0.5, then that would be the case, and all these 16 outcomes would have the same probability. However, here we're solving for the more general case where p is unnamed, so it could take on any value between 0 and 1. But there is one thing we do know. Within these groups that we have isolated here, for example, these 4 outcomes and this second group, those 4 outcomes would all be equally likely because they all contain 3 heads and 1 tail. And the order on which the tail happens doesn't matter because the trials are IID, the tosses are IID, independent and identically distributed. That is also the case for this group of 6 here. Each of these elementary outcomes must have the same probability. And as you can see, that is the case for each of these 5 groups. You may notice that the numbers on the left might remind you of Pascal's triangle. And that is indeed the case. This 1 here is really a 4 choose 0, this 4 is a 4 choose 1, this is a 4, the 6 is a 4 choose 2, the 4 here is a 4 choose 3, and the 1 is a 4 choose 4. Let's just take one outcome and see what its probability is. What's the probability of getting heads, tails, heads, heads? Well, the probability of heads is 1 minus p, the probability of tails is p, probability of heads on the third toss is 1 minus p, and then we got one more head, and that's 1 minus p. Now the order of multiplication certainly doesn't matter, so we can write this as p to the power of 1 times 1 minus p to the power of 3. Okay, so that's the probability of this third outcome here, but there are 4 of them here, right? And this 4 choose 1 gives us that count of 4. So hopefully you can now see that the PMF of the binomial random variable is really just a counting exercise where we're counting equally likely outcomes, each of which has probability p to the power of x times 1 minus p to the power of n minus x. You should see this 1 here as x and this 3 as n minus x, where n is 4 in this case and x is 1. Every legitimate standardized PMF should add up to 1 if we were to sum the PMF over all possible values in the support of the random variable. In this case, we have a binomial NP random variable, and if we were to sum the PMF over all possible values of this random variable, in other words, all lowercase x in the support of the random variable x, we should get 1. But how do we convince ourselves that this is indeed the case? So let's take a look at this sum. So we want to sum n choose x times p to the power of x times 1 minus p to the power of n minus x. And we want to sum it over the entire support of the random variable x. Recall that x can be thought of here as the number of tails in n tosses. So what are the possible values of x then? Well, we could get x to equal 0, right, if we get heads on every single toss. We could get it to equal 1, 2, 3, and so forth, up to n, the case in which every toss ends up in tails. And this one may be just a little bit trickier to recognize than the following. I'm going to write this sum again, but instead of p and 1 minus p, I'm going to use a for p and b for 1 minus p. Now, you may recognize this as the binomial theorem. In fact, that is where the name binomial of this distribution comes from. Binomial refers to the sum of two terms, a and b here, that in this case are raised to the power of n. So this is the binomial formula. And you've used it, I'm sure, plenty of times when, for example, evaluating a plus b to the second power, that's a squared plus 2ab plus b squared, and this, where these terms can be viewed as this is 2 choose 0 times a to the power of 2, b to the power of 0. The second term is 2 choose 1 times a to the power of 1 and b to the power of 1. And this last one here is 2 choose 2 times a to the power of 0 and b to the power of 2. So then in this above expression that we're trying to evaluate, we have essentially the binomial formula, but a equals p here and b equals 1 minus p. Therefore, this will evaluate to p plus 1 minus p, that's the binomial in question, raised to the power of n in this case. Okay, but what do we have here inside the parentheses? Well, p minus p is 0 and we're left with just 1, so this equals 1 to the power of n, which is just 1. and we have shown what we were trying to show, that the PMF of the binomial random variable indeed sums to 1 over the support of the random variable. Now imagine that in the course of solving for something, we run into this expression in green, and we need to evaluate it. What does it evaluate to? Suppose that we had a random variable x with the binomial distribution, but this time with parameters not n and p, but n minus 1 and p. Like before, this means that we can interpret x as counting the number of tails in n minus 1 tosses of a coin, where the probability of tails on each toss is p. Okay, so then what is the PMF of x? Well, it's supposed to be n choose x, right? But in this case, instead of n, we're going to write n minus 1 because that's the first parameter now. So n minus 1 choose x. Okay, and then the next thing was what? P to the power of x times 1 minus p to the power of, used to be n minus x, but in this case it'll be n minus 1 expression minus x. Notice now how close this PMF in yellow is to the expression here that we're summing. And take a look, we are summing it over x going from 0 to n minus 1, and a binomial n minus 1 p random variable will take on values from 0 up to n minus 1, right? If we were tossing a coin n minus 1 times, the number of tails we could get would go from 0 to n minus 1 in increments of 1. Essentially what we have here is the sum of the PMF of a random variable over its entire support. Therefore, it must equal 1. And we're done with evaluating the expression in green, which looked so intimidating at the beginning. It will be important for us to be able to recognize PDFs, PMFs of random variables with slightly different parameters than the ones that we are used to seeing. This was our first example kind of in this category, but there'll be a lot more. Let's see now if we can evaluate the expected value of this random variable x. By definition, the expected value of a discrete random variable, like our binomial over here, will be the sum of the values that this random variable can take, denoted by lowercase x, times the PMF evaluated at each lowercase x, and the summation needs to go over the entire support of the random variable x. Okay, now let's replace the expression for the PMF in here and choose x times p to the power of x times 1 minus p to the power of n minus x. And instead of the generic index here going over the entire support of x, let's think about what the support of x is here. We know that x can go from 0 to n in integers in increments of 1. So therefore x will go from 0 to n. Okay, so this is the expression we're trying to evaluate. Now, it isn't immediately clear how to proceed with this, but it turns out that this expression here can be simplified in a way that will be very advantageous for us. So let's have a look at it in close-up. So let's unpack what n choose x is. We know that that's n factorial over x factorial times n minus x factorial. And we can cancel an x there, and what we're left with in the numerator is n factorial, and in the denominator we'll have x minus 1 factorial times n minus x factorial. Now, it isn't immediately clear here what we'd want to do because the destination isn't clear, but imagine that we had the foresight to pull an n out, then what would be left with in the numerator is n minus 1 factorial, and in the denominator x minus 1 factorial times n minus x factorial. Now this expression here, if we were to just look at it for some time, we'll see that it is n minus 1 choose x minus 1, right? Because think about what that would be. And the numerator would have n minus 1 factorial, and that's indeed what we have here. And the denominator will have x minus 1 factorial, and then we'll need the difference. So it'll be n minus 1 minus x minus 1, but what does that evaluate to? Is just n minus x, because the minus 1 with the plus 1 will go away. Okay, so that is pretty cool now, because we have shown that this expression here on the right equals n times n minus 1 choose x minus 1. And you may ask yourself, okay, I mean, how much better is that? And that's fair, but this original expression here wasn't going anywhere. So at least we got something that we can try now. But first, let's remind ourselves that a combinatorial term of the form n minus 1 choose x minus 1 requires that n minus 1 be greater than or equal to than 0, x minus 1 be greater than or equal than 0. Both of these numbers have to be integers, and furthermore, n minus 1 needs to be greater than or equal than x minus 1. So the first condition here would give us that n must be greater than or equal than 1, and the second one that x must be greater than or equal than 1, and n must be greater than or equal than x. So that is also implicit in this starting expression, so I won't write that out. Okay, so we can substitute this expression we derived for the original expression only if we're dealing with a situation where n is always greater than or equal than 1 and x is greater than or equal than 1. So we need to keep that in mind. With that in mind, let's decompose the sum we're trying to evaluate into two terms. The first one, which will be a summation over only one value of x when x is 0. So we're saying as x goes from 0 to 0, basically it'll be just one value. There's nothing wrong with writing it this way. We have p to the power of x times 1 minus p to the power of n minus x. And then the leftover, which is most of it, the sum as x goes from 1 to n of the same thing, x times n choose x times p to the power of x times 1 minus p to the power of n minus x. Okay, and why did we do that? Well, because these conditions, n always greater than or equal than 1 and x greater than or equal than 1, are satisfied for the second term, but not for the first. So we could substitute this expression we derived in the second term, but not in the first. Okay, but what's the deal with the first one? So this one is to be evaluated when x equals 0. But notice that x enters the expression here under the summation sign, multiplying whatever is left. So we'll get 0 here when x is 0. So this first term will be 0. Okay, that's very nice. And now in the second one, let's express this expression here with, let's replace it with the one we derived. So we get sum as x goes from 1 to n of n times n minus 1 choose x minus 1 times p to the power of x times 1 minus p to the power of n minus x. It isn't immediately clear where this expression is taking us, but let me first make some room here. But if we looked at it long enough, we'd probably figure out that we could pull out a couple terms and things become interesting. In particular, we can pull out this n, right, which is a constant. We can pull it out of the summation, not a problem. And we can pull out 1p from this p to the power of x. And then what we have inside the summation sign is x going from 1 to n of n is gone because we pulled it out, n minus 1, choose x minus 1, times, now having pulled out 1p, we have x minus 1 of them left, and there's still a 1 minus p to the power of n minus x. This expression here is kind of looking like a binomial distribution summed over its support, but not quite, because every binomial random variable can take on the value 0, right? You can always get 0 tails in however many tosses. So we would need this summation to start at 0. Okay, so let's introduce a variable k, another index variable, which will take on values x minus 1. So when x is 1, k will be 0. Okay, so then what is it that we have here? N times p times the sum, as k goes from, when x is 1, k is 0, and when x is n, k is n minus 1. And what are we summing over? N minus 1, choose, instead of x minus 1, we put k, right? We're replacing x everywhere here with k. P to the power of k times 1 minus p to the power of n minus x. So what is this n minus x? Well, what is x? X would be k plus 1. So what we have there is n minus k minus 1. And let's just write it as n minus 1 minus k. Okay, so that's the power to which 1 minus p is raised, n minus 1 expression minus k. And why is this interesting? Well, because now this summation here, look at it carefully, is a summation of the PMF of a particular binomial random variable over its support. So think of a random variable x that has the binomial distribution, but with parameters not n and p, but n minus 1 and p. So think of what its PMF would look like, right? You know, kind of the standard one, but now we're replacing n with n minus 1, and that's exactly what we have there in the combinatorial term. And our index variable here is k. Okay, that's fine, doesn't matter what letter is used for the index variable. P is then raised here to x, here is raised to k. Okay, so that looks good. And 1 minus p is raised to what? N here, which is the first parameter, and n minus 1 here, the first parameter, and we have a minus x, and then here it's a minus k. Perfect. So this expression here indeed is the sum of a binomial n minus 1 p random variable over its entire support, because right, the support of such a random variable would go over the integers 0, 1, 2, 3, and so forth up until n minus 1, right, because there are n minus 1 trials here. Okay, very good. So then we know that this sum must evaluate to 1. So what we really have is n times p times 1. And that completes our effort here. We have shown that the expected value of a binomial np random variable is np, the product of those two parameters. Pretty cool. Okay, we looked at a discrete random variable. Now let's take a look at a continuous one. Let's take x to have the uniform 0-1 distribution. This means that its PDF, or the PDF of x, would be 1. right? Where x, the support of x, would be the closed interval between 0 and 1. And to verify that we got the PDF correct, we can try integrating it on the support, and we know that we should be getting 1, right? So what is the support? It's the interval from 0 to 1. So if we integrate the PDF of x on this support, we should be getting 1. Okay, let's replace the PDF with its value, which is just 1, and the integral of 1 is just x, and the limits of integration go from 0 to 1, so we get 1 minus 0, and that's 1. Okay, so this is a valid PDF. When we integrate it over its support, we get 1. Okay, now let's compute the expected value of this random variable. The expected value of x, by definition, would be the integral of x times the PDF of x, evaluated lowercase x, over the support. And the support is the interval from 0 to 1. So that's what we have, and we need a dx here. Okay, so this is what we're trying to evaluate. Let's replace the PDF with its actual value, which is just 1. So this is what we're looking to integrate. The integral of x is x squared over 2, and the limits of integration are 0 to 1. So we get 1/2 minus 0, and that's just 1/2, which is 0.5. And does it make sense? Suppose that this is our interval from 0 to 1. Our PDF is constant at 1 over this interval. And we have just worked out that the expected value then is 0.5. Makes intuitive sense. Okay, we have just looked at one example of a discrete random variable and one example of a continuous random variable. For the discrete one, we looked at a binomial NP random variable, and we worked out its expected value to be just n times p. And for a continuous one, we looked at a uniform 0,1 random variable, and we worked out its expected value to be 0.5. But notice from this definition that this expression in A, which we evaluated for the uniform 0,1 distribution, and this expression in C, which we evaluated for the binomial NP distribution, these expressions constitute legitimate expectations only if these conditions on the right hold, B and D. This condition in B can be seen as being just the expected value of the absolute value of the random variable x. And same here. So in other words, notice that the expected value of x is legitimate only if the expected value of the absolute value of x is finite. And we never bothered to check the conditions B and D. Luckily, we don't have to do that. Notice that we've worked out through example A and B here. And these are in the first row. And I have that first row labeled as expected value of x guaranteed to exist. For random variables like the binomial that have a finite support, the expected value of x is guaranteed to exist. In other words, the expected value of the absolute value of x is guaranteed to be finite. And for random variables like the uniform 0,1 that have a bounded support, right, the support is bounded between 0 and 1. It doesn't extend to negative infinity or to positive infinity. So for such random variables with a bounded support, once more, the expected value of x is guaranteed to exist, and we do not need to check on the expected value of the absolute value of x. In the case of a discrete random variable taken on finitely many values, it is very straightforward to see why the expected value would always converge. The expected value is nothing other than a weighted average, and in this case it'll be a weighted average of finitely many finite values, and so it will always be a finite value. Therefore, whenever we have a discrete random variable taking on finitely many values, which is the situation we explored here in row 1 for discrete random variables, the expected value is guaranteed to exist. And both the expected value of x and the expected value of absolute value of x are guaranteed to converge. The situation is very similar for continuous random variables that have a bounded support, because think about it, for those random variables, the highest possible value that the random variable can take on is the max of that bounded support, which is a finite value. So the expected value of x can be at most that finite value. Therefore, it won't be infinite. So once more, in the case of continuous random variables with bounded support, both the expected value of x and the expected value of the absolute value of x are guaranteed to converge. Therefore, the expected value of x is guaranteed to exist. Okay, so these are the type of variables that we studied here in row 1. It's time now to move to row 2 and look at slightly more tricky random variables. In example C, we'll look at a random variable with a geometric distribution. Unlike the binomial distribution, the geometric distribution does not have a finite support. In other words, a geometric random variable takes on infinitely many values. And in examples D and E, we'll look at random variables with the exponential and Pareto distributions. These distributions, unlike the uniform distribution, do not have a bounded support. In the case of these two distributions, both of them extend into positive infinity. For these, the expected value of x is not guaranteed to exist. However, we will show that if we work out the expected value of x to be finite, then the expected value of the absolute value of x, that condition that needs to hold, will hold automatically. And that is because variables like the geometric or the exponential are one-sided. So for one-sided random variables, those that take on only non-positive values or non-negative values, the expected value of x being finite automatically guarantees that the expected value of the absolute value of x is also finite. Okay, well, let's take example C and look at it in more detail. Okay, so we have a random variable x with a geometric distribution with parameter p, and we want to find its expected value. But before we do that, let's talk about how a random variable with a geometric distribution arises. It arises in the same context as the binomial random variable, the context being IID trials. Just like with the binomial, a geometric will always arise in the context of IID Bernoulli trials. So, whereas the binomial was keeping track of the number of successes in n trials, a geometric random variable will keep track of the number of tosses required for us to get the first success. So if we're considering tails to be the success, then with the binomial, it was keeping track of the number of times we get tails in n tosses of a coin. But now with the geometric random variable, it's going to keep track of the number of tosses required for us to get tails for the first time. And from that story alone, it is clear then that the smallest possible value that x can take is 1. Because, so we said that x here is keeping track of the number of tosses required for us to get tails for the first time, and it will take at least 1 toss for us to get tails for the first time. But it may take 2 tosses. So an x of 2 basically means that we get tails on the second toss, which implies that we did not get tails on the first one. So essentially, an x of 2 means we get heads on the first toss and tails on the second toss. But x can also take on the value 3 and 4 and so on. It is theoretically possible that we never get tails for the first time, that every single toss. We would toss it infinitely many times, and every time it turns up heads. Okay, and as always, P needs to be a legitimate probability, so it needs to be between 0 and 1. Okay, now what is the PMF of this random variable? The PMF of this random variable is quite straightforward from the story alone, because we know that we have IID Bernoulli trials, and we know that X gives us the number of tosses required until we get tails for the first time. So if we're going to get tails on the Xth toss, lowercase x, then the preceding tosses must have all been heads. How many preceding tosses are we talking about? X minus 1, and with the probability of heads being 1 minus p, there will need to be x minus 1 of these. And because they're all independent trials, we can multiply these probabilities, and then we'll get tails on the xth toss. So we need a p here raised to the power of 1, but I don't need to write that power of 1. So this is the PMF of the geometric random variable. And it, I think, is a good idea to check that any PMF we use is a legitimate one and actually sums up or integrates to 1 over the support. So let's verify that if we were to sum this PMF over its support, that we do get 1. So the support is x going from 1 to infinity. P is a constant, so we can pull the p in front of the summation sign. And what we have left in there is 1 minus p to the power of x minus 1. And if the name of this series didn't give it away, looking at the sum here should remind us of the geometric series. The geometric series, if you recall, looked like this: r to the power of 0 plus r to the power of 1 plus r to the power of 2 plus r to the power of 3, and so on and so forth, equals 1 over 1 minus r, where the absolute value of r needs to be less than 1. In other words, r needs to be strictly between minus 1 and 1. Okay, so this is the geometric series formula. And let's just recognize that here on the left side, if we were to write it with the summation sign, we have the sum as x goes from 0 to infinity of r to the power of x. So then we can continue this evaluation here, recognizing that our 1 minus p plays the role of r. There's one little problem in that our index variable x here starts at 1, but in the geometric series formula it starts at 0. So we just need a different index variable. So let's say that we'll use an index variable of k, which will take on the values x minus 1. So then the summation here can be rewritten in terms of k. When x is 1, k is 0. When x is infinity, k is infinity. And it's the sum of 1 minus p to the power of x minus 1, which is just k. Okay, and now this summation over here is exactly the summation we got in the geometric series, with 1 minus p playing the role of r. Therefore, we can replace it with this value from the right, so we get p times 1 over 1 minus, and instead of r, we'll write 1 minus p. And then in the denominator, you'll see that we have this 1 minus 1, so that's 0, and there's a minus p, which is just p, and so we have p times 1 over p, and that's just 1. Okay, so we have shown that this is a legitimate PMF in that it sums to 1 over the support. Okay, so now we are now ready to evaluate the expected value of our geometric random variable, and so by the formula it is the sum of lowercase x times the PMF of our random variable, and I'll just replace its value 1 minus p to the power of x minus 1 times p, and the summation needs to go over the entire support, which is from 1 to infinity. Okay, now as before we see that there's a constant here. Let's pull it in front of the summation sign, and we have this left. Okay, now this is a little tricky here, and we just need to kind of try different things here, and eventually we might notice the following. There's an x here, and then the exponent is x minus 1, and that might just remind us of the fact that if we were to take the derivative of t to the power of x, that we would get x times t to the power of x minus 1. And you see that now, and you see that maybe taking derivatives here would somehow get us what we need. And then this kind of looks like a geometric series, right? So eventually we may arrive at the brilliant idea of taking the derivative of both sides of this geometric series identity. Okay, so let's try doing that. So the derivative of the left side will give us the derivative of R0, which is derivative of 1 is just 0, so we don't need to write that. The derivative of R is 1, plus the derivative of R squared is 2R, plus the derivative of R cubed is 3R squared, and so on and so forth. And then on the right side, this is 1 minus R to the power of minus 1. So when we take the derivative of that, we get a minus, and then 1 minus R to the power of minus 2. So that's 1 over 1 minus R squared. And by the chain rule, we still need to take the derivative of 1 minus R, which is minus 1. So there'll be a minus, another minus sign, essentially making this minus in front of plus. Okay, so I'll just erase this plus. And now let's see what it is that we got. So we got this identity here from taking the derivative of both sides of the geometric series. And how helpful is it? Well, it looks quite helpful, but perhaps to see it better, let's write this left side in summation terms. So if we used an index variable of x, and let it start at 1 and let it go through infinity, what is it that we'll need to sum for us to express this left side in summation terms? Let's see, when x is 1, we need to get a 1. So it looks like an x might belong there. Okay, but I'm not sure about what else. Let's take a look at x taking on the value 2. When x is 2, we need to get 2r. So the 2 will be given by x, but we still need the r. And let's go back to x equal 1 and see if we're still okay. When x is 1, xr will be 1 times r. And so we're not okay unless r was raised to the power of 0. Okay, so we're just going to keep that in mind. And 0 is 1 less than 1. Okay, when x is 3, this would be the 3, and then we need an r squared, so that r needs to be raised to the power of x minus 1. Okay, and then I think that now that works for x equal 1, right? For x equal 1, we get this to be 1 times r to the power of 0, that's just 1. When x is 2, this is going to be 2 times r to the power of 1, which is good. When x is 3, this will be 3 times r to the power of 2. Okay, that works. So we've written the left side in summation terms, and in fact it is so much more useful than what we had in there that I will just bring it in here. So the sum as x goes from 1 to infinity of x times r to the power of x minus 1 is that. Okay, and that is exactly the identity we needed, right? Because if you just replace this r with 1 minus p, let's look at it for a moment, this identity is exactly what we need. So then what is it that we get? We have p times what? So this whole summation sign here can be replaced by the right side here, where instead of r we'll use 1 minus p. So we get 1 over 1 minus, instead of r we put 1 minus p, whole thing squared, and we get p times 1 over this 1 minus 1, that'll be 0, and then minus p, that's just p, and it's squared, so we get p times 1 over p squared, and that's 1 over p. Okay, so that is the expected value of our random variable. So if x is a geometric random variable with parameter p, its expected value is just 1 over that parameter, 1 over p. Okay, next let's take a look at a random variable that has the exponential lambda distribution. The exponential family of distributions is indexed by one parameter, lambda, so different values of this parameter will give us different members of this family. But in this case here, we're working with the generic case where we don't specify a particular value of lambda. But by definition, lambda has to be positive. Okay, and here's the PDF of an exponential lambda random variable, and here's the support. And you can see that the support is between 0 and positive infinity. Okay, as before, let's start by verifying that this PDF does indeed integrate to 1 over its support. So the integral from 0 to infinity of the PDF, which is 1 over lambda times e to the power of minus x over lambda dx. Okay, so we want to evaluate this integral. This is a relatively straightforward one, so we might notice right away that this is what we would get. But if we don't, we can always verify it. So what is d dx of minus e to the power of minus x over lambda? Well, it will be minus e to the power of minus x over lambda, so the first the term itself, then the derivative of the exponent, which is minus 1 over lambda, and then notice that this minus sign from here and this minus sign will give us a plus, and so we have this 1 over lambda times e to the power of minus x over lambda, and that's exactly what we were trying to integrate. Okay, so then we did integrate this correctly. Okay, so now this expression evaluated at infinity will give us minus e to the power of negative infinity over lambda. E raised to the power of negative infinity is going to give us 0. And then when x takes on the value 0, e to that whole exponent will give us 1. But we gotta be careful with the minus sign here. So there's a minus first, and then there's a minus 1. And so we'll put it all together, and the two minuses give us a plus, and we verified that it does indeed integrate to 1. Okay, and now let us evaluate the expected value of this random variable. So the expected value of x, by definition, is the integral of x times the PDF dx, and it's over the support, so from 0 to infinity. And it's pretty clear here that we're going to need to integrate by parts. So if you don't remember what that is, there's a formula that says that integral of u dv equals u times v minus integral of v du. So let's let x be u, and 1 over lambda times e to the power of minus x over lambda dx be our dv. That means that dx will be du, and from here we have, now we need to integrate this, and we've already looked at it before, and so v will have to be, let's see, it will have to be minus e to the power of minus x over lambda. Right? Doesn't make sense. We've integrated both sides on the left. So if we were to take the derivative of this, we've got a minus here in front and a minus in the exponent, which will give us a plus. And then we'll have the 1 over lambda and e to the power. Okay, so that looks correct. Okay, so then by using the formula of integration by parts, what is that we get? We get that we have uv first, which is x times minus e to the power of minus x over lambda. I should put the limits of integration here, limits of evaluation, minus integral from 0 to infinity of v du, and that is minus e to the power of minus x over lambda, and du is just our dx. This first expression is quite straightforward to evaluate, because when x will go to infinity, this term here on the right will be 0. And then when x will take on the value 0, the first term will be 0. So in either case, that first expression will be 0. So that one goes away. Now we just need to deal with this integral here. And notice again that we have a minus sign in front and a minus here, which will combine to a plus. So really all we have is the integral from 0 to infinity of e to the power of minus x over lambda dx. And we've already done this one. Well, almost. We don't have a 1 over lambda this time, so we have to keep that in mind. So what do we get? I think we're going to get lambda, but we'll need a negative sign in there too. So we need a minus lambda times e to the power of minus x over lambda, evaluated from 0 to infinity. Does that look right? So when we take the derivative of this, do we get this expression? So that looks correct. Okay, so when x goes to infinity, e will be raised to the power of negative infinity, and that will give us 0. So that first term is 0, and then minus, and then when x takes on the value 0, e to the power of minus x over lambda will be 1, and so and we have a lambda still here, so that will be minus lambda, and therefore these two minuses combine to a plus, we have that the expected value of this random variable equals lambda, just the parameter of this exponential distribution. Next, let's have a look at the Pareto family of distributions. This is a fascinating family of distributions for many reasons. All the distributions we have looked at so far have an expected value for all values of the parameters. The Pareto family of distributions takes two parameters, alpha and beta, where alpha is also referred to as the minimum value, because if you take a look, alpha plays the role of the minimum of the support of this distribution. And the second parameter, beta, is a shape parameter that directly controls how much area is in the tails, or the thickness of the tails. And it'll be of great interest to us in this exercise here. So, okay, well, let's do the usual. Given a PDF, we should be able to verify that it actually integrates to 1 over the support. So the support here goes from alpha to infinity, and the PDF is beta times alpha to the power of beta over x to the power of beta plus 1 dx. So there's a lot of letters here, but x is the only one that we're integrating here with respect to, so this is quite straightforward, right? We can just pull the constants in front. We got beta times alpha to the power of beta times the integral of, and I'll write the x with a negative exponent, minus beta minus 1 dx from alpha to infinity. Okay, and what do we get? We get beta times alpha to the power of beta, and how do we integrate this? Well, this one is quite straightforward to see that if we had x to the power of minus beta over minus beta, and if we took the derivative of this expression, then we would get x to the power of minus beta minus 1. Okay, so that looks good, and we need to evaluate this from alpha to infinity. Let's note a couple things here. One is, you notice that the beta, we have a minus beta here in the denominator, but alpha and beta are strictly greater than 0, so we don't have a problem with division by 0 here. Okay, that's good. And then what about here in the actual PDF? X is in the denominator, but notice that x is always greater than or equal than alpha, and alpha is strictly greater than 0. So again, we do not have a problem of dividing by 0 at any point in time. Okay, that's important. So let's try to evaluate this. So let's try to simplify it first, and then we'll evaluate it. So we got a beta here and a beta here that will go away, and what we have left is minus alpha to the power of beta times x to the power of minus beta. Okay, so evaluated at infinity, x to the power of minus beta, so infinity to the power of minus beta, will be what? Well, beta is always greater than 0, so minus beta is always strictly less than 0. So infinity to a negative power is going to give us 0. So we'll have 0 minus, when we plug alpha for x, we will get minus alpha to the power of beta times, instead of x we plug alpha, and we get alpha to the power of minus beta. Okay, well that's quite nice. The minus with the minus here will go away, and we'll have a plus, and then with the alphas the power will be 0, and we'll get a 1. Okay, so notice what we have shown. We have shown that for all sets of parameter values where alpha and beta are strictly greater than 0, this is a legitimate PDF. It always integrates to 1. Right? Let's keep that in mind. Now let's investigate its expected value. The expected value of x, by definition, will be the integral over the support, which goes from alpha to infinity of x times the PDF of x So let's write that out, and then we just need a dx, and we are good to go. Okay, so what can we do here? Well, first there's a little cancellation here with regards to x, and then we can pull the constants in front of the integral sign. Okay, so we'll have beta times alpha to the power of beta times the integral, as it goes from alpha to infinity of, in the denominator we'll have x to the power of beta, and so we can write that as x to the power of minus beta. Okay, so this is where we need to be careful. It might be tempting to apply the power rule here, but we have to be careful because the integral of x to the power of minus 1, or in other words, the integral of 1 over x, is log of x, right? Then this is not obtained by the power rule. Whereas for all other values of the exponent beta, this integral can be evaluated using the power rule, right? So we would need what? We would need x to the power of minus beta plus 1 over minus beta plus 1, right? So if we take the derivative of what's here on the right, we get x to the power of minus beta. But this is for beta different than 1. Okay, so then in our integral here, there will be two cases corresponding to beta equal to 1 and the other one for beta different than 1. And beta different than 1 can be combined with the fact that we know that beta needs to be strictly greater than 0. So I'll just rewrite this as beta greater than 0, strictly less than 1, or beta greater than 1. Right, so that's the second case. So case 1, beta equal to 1. Case 2, beta is different than 1. Let's take that first case first. So the case when beta is equal to 1. Then what is it that we get for this integral here? Well, then we get that the expected value of x is beta times alpha to the power of beta times, and now this integral just becomes the log of x, and this needs to be evaluated from alpha to infinity. And notice that when x goes to infinity, we get infinity, and when x takes on the value alpha, we'll get some constant c, but infinity is so much larger than any constant, so we'll end up here with infinity. Okay, so when beta equals 1, the expected value does not exist. That's very interesting, but it gets more interesting. Let's take a look at the second case. So now, when beta is different than 1, let's try to see what the expected value of x will be. We get beta times alpha to the power of beta times, and now we'll use the power rule. So we have that x to the power of minus beta plus 1 over minus beta plus 1. Okay, and the limits of integration are alpha to infinity. Now, let's see if we can make sense of what happens when x goes to infinity. When x goes to infinity, we have infinity raised to the power of minus beta plus 1. And all we know here is that beta is different than 1. Okay, but beta can still be less than 1 or can be greater than 1. And if beta is less than 1, then this exponent will be positive. And if beta is greater than 1, then it'll be negative. And that will make a world of a difference for us here, right? So we see then that we need to further split here into two cases. So case 2a and case 2b. In case 2a, we'll look at beta strictly between 0 and 1. In case 2, beta strictly greater than 1. And again, the reason we do that is because that exponent will change signs, and we need to know what sign it has. Let's do the case 2b first. So when beta is greater than 1, this exponent here, minus beta plus 1, will be negative. And so then as x goes to infinity, it'll be raised to a negative power, and then we're going to get 0 in that case. Okay, so as x goes to infinity, we get 0. And now as x takes on the value alpha, what is it that we get? Well, we'll just have to write it out. It's beta times alpha to the power of beta times alpha to the power of, and I'll write it as 1 minus beta over 1 minus beta. Okay, ran out of space, so I'm just going to write it over here. So we have alpha raised to the power of beta times alpha raised to the power of 1 minus beta, which will end up with just an alpha raised to the power of 1 multiplied by that beta in front. So we'll have minus alpha beta in the numerator and then 1 minus beta in the denominator. And it can be expressed even more neatly if we just combine the two negative signs to flip the sign in the denominator, and then we get, for the expected value of x, alpha times beta over beta minus 1. So putting it all together, the Pareto family of distributions is special because we've shown, first of all, that it integrates to 1 for any value of the parameters, any acceptable value of the parameters, where acceptable here means that alpha and beta both have to be strictly greater than 0. But we have shown that only if beta is greater than 1, then we get members of this family that actually have an expected value defined. If beta is strictly greater than 0, but less than or equal than 1, then we get members of this family of distributions that do not have an expected value. In a little bit, we'll look at the Cauchy family of distributions. There, the situation will be very different. In the case of the Cauchy family of distributions, the expected value does not exist for any member of that family of distributions. Before we turn the page on the Pareto distribution, let's connect the fact that that second parameter, beta, is referred to as the shape parameter and is supposed to control how much area there is in the tail of the Pareto distribution. You can tell from the support of this distribution, right, which is between alpha and positive infinity, that the Pareto distribution will have only one tail, the right tail. So this parameter beta is going to control how much area there is in the tail. So let's see an animation of that. Our starting point will be the Pareto 2-2 distribution, and here's what that looks like. Now let's take a moment to connect the visual to the math. The PDF of the Pareto distribution, we said, is beta times lambda to the power of beta over x to the power of beta plus 1. And the support of this distribution is the interval from alpha to infinity, where alpha and beta both have to be greater than 0. Okay, we've written down the PDF for this entire family of distributions, and now let's look at a particular member of this distribution, the one with alpha and beta both equal to 2. So let's just replace beta with 2 and alpha with 2, so we have 2 times 2 to the power of 2 over x to the power of 2 plus 1. So in the numerator we have 8, and in the denominator x cubed, and we can just write it as 8 times x to the power of minus 3. That's the PDF. And what's the support? Well, with alpha equaling 2, the support will go from 2 to infinity. Okay, great, and now let's connect this to the visual. Notice that this segment here is outside the support. We're at 0 here. A complete description of the PDF would include that part where the PDF is 0. And let's verify one thing. We have here this statement that the probability that x is greater than or equal than 4 is 0.25. Essentially, we're saying that the area under the tail to the right of 4 is 0.25. So that would be straightforward to verify because we have the PDF, and then if we integrated it from 4 to infinity, right, so we just need to integrate the PDF from 4 to infinity. And here's the PDF. When we do that, we should be getting 0.25. And how do we do that? Let's pull the 8 in front, and then we have integral of x to the power of minus 3 dx, and we get 8 times x to the power of minus 2 over minus 2. Right? When you take the derivative of this, you get x to the power of minus 3. That looks right. And we go from 4 to infinity. Okay, so what we really have here is minus 4 over x squared, evaluated from 4 to infinity. And at infinity we get 0, and at 4 we get minus 4 over 16, and that is 1/4 or 0.25, and that matches what Python told us here that the area to the right of 4 is. And we'll now be aware of the fact that there's quite a bit of area in the right tail of the Pareto 2-2 distribution. Now what happens as we change the value of the parameter beta? Let's take a look. Notice that as the value of the parameter beta decreased from 2 to 0.2, the area to the right of 4 increased from 0.25 to 0.87. And at this point, this plot is really deceiving because there's no way that we can see here that to the right of 4 there's 87% of the area under this PDF. But we know from the math that this is the case. So as the value of the parameter beta decreases, the tails become fatter. There's a larger percentage of the area in the tails. And recall that we've shown that for the members of the Pareto distribution with beta less than or equal than 1, the expected value does not exist. And now we see the full story. As the value of the parameter beta decreases, and as it decreases, crossing that threshold at 1, as it decreases below 1, the tails become fat enough that sufficient weight is placed on really high values in the very tail of this distribution that it throws off the weighted average, which is the expected value. It throws it off because basically for that weighted average we get infinity and not a finite value. And that is why we say that the expected value for members of the Pareto family with beta less than or equal than 1 does not exist. As we let the value of the parameter beta increase, the tails will start thinning out to the point where we cross that threshold, which to the eye doesn't mean anything. But we know that for a value of beta strictly greater than 1, the tails are thin enough that the expected value does exist. And then recall that we said that the parameter alpha is also the minimum of the support of this distribution. So as we change the parameter alpha, the minimum of the support of this distribution is going to shift accordingly. And that's the story of the Pareto distribution. Let's briefly recall the definition of the expected value, and in particular the fact that the expected value of x is said to exist only if the expected value of the absolute value of x is finite or converges. But we just looked at 3 examples here in row 2, right? We looked at the geometric, the exponential, and the Pareto distributions. And in all of those cases, we directly computed expected value of x. We did not bother checking whether the expected value of the absolute value of x converges or is finite. So do we have to go back now and do all of that to be sure that the expected value of x exists? Luckily for these 3 distributions, the geometric, exponential, and Pareto, as well as any other distributions that are like these in row 2, which we've labeled as one-sided random variables that take on only non-positive or non-negative values, if we establish that the expected value of x is finite, then that automatically guarantees that the expected value of the absolute value of x is also going to be finite, so we don't even need to bother checking it. So we've had it good here in row 2, but it is time now to look at row 3, where we will look at random variables that take on both negative and positive values. We'll look at discrete random variables that take on infinitely many values and whose support is not one-sided. And we'll look at continuous random variables that extend into both negative infinity and positive infinity. In other words, again, random variables that are not one-sided. For these, working out the expected value itself is not sufficient. We will have to go back and also verify that the expected value of the absolute value of x is finite. Okay, what follows is probably my favorite part of this section, and honestly it's material that I haven't seen covered in any probability book, and yet it is the very heart of the reason of why we require absolute convergence in order for the expected value to exist. So let's build to it gradually. So suppose that we have a random variable x, which will take on the values 1, minus 2, 3, minus 4, 5, minus 6. So essentially the integers from 1 to infinity, but for the even integers we put in a minus sign. Okay, and these go on into infinity. Okay, and notice that they'll go to both positive and negative infinity, right? So pretty tricky situation here. Okay, and then for the PMF of this discrete random variable, let's take the following. We'll take it equal to 6 over pi squared times x squared. Okay, so this is our random variable x, and these are the values it takes on, and this is its PMF. So before we verify that it's a legitimate PMF by making sure that it sums to 1 over its support, notice that just thinking in terms of support here, it's very difficult because the support goes from over the integers from negative infinity to positive infinity. Is it possible for us to re-express this random variable so that its support would, or that not the sort of support, but so that in the summations we would sum over only, say, the positive integers? And there is a natural thing that we can do here. So for odd indices, this is 1, 3, 5, we want the power to be even. So if n was the index and we took n plus 1 for the power, they'll do, because then for odd indices this will evaluate to 1 and we get the positive sign. And then for even indices, n will be even, n plus 1 will be odd, and then this will evaluate to minus 1. Okay, so we've taken care of the sign, and then we just need to multiply it by n, right? So that's the general expression for the values that x takes on. And the beautiful thing now is that here n goes over only the positive integers, which will make our life easier. And notice that this PMF can also be expressed in terms of n. So notice that x enters here as x squared, right? So these are the values we're squaring, but in squaring the sign doesn't matter, right? So we could alternatively write n squared there, right? Because n squared and x squared is going to give us the same thing. So now we have re-expressed this problem, which had a support going from negative infinity to positive infinity over the integers in terms of n, where n goes over only the positive integers, and we've re-expressed the PMF in terms of n as well. Okay, now next we will need to recall some results from calculus, which I won't rederive here because they'll take us astray too far, but we do need to know the results of these. So the first one is the harmonic series. The harmonic series looks like this. It starts with 1, and then it adds 1 over every positive integer. And so when we do that, let's write it as summation. This is the sum of 1 over n, right, as n goes from 1 to infinity. So the harmonic series famously diverges. In other words, the sum is infinity, and we say that this series diverges. It does not have a finite value. But a close cousin of the harmonic series, which is called the alternating harmonic, where we alternate the signs, this one famously does converge. And if we were to work it out, it'll give us log of 2. And we need one more. And this last one is 1 over, so if we were summing 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus and so on and so forth, where you see what we're summing here. We're summing 1 over n squared as n goes from 1 to infinity. This series also famously converges, and it equals pi squared over 6. And I've forgotten to write this second one as a summation, so let's do that. It's the sum of minus 1 to the power of n plus 1. So as n equals 1, the exponent here is going to be 2, and minus 1 raised to the power 2 will give us a positive sign. Okay, so sorry, we've only taken care of the sign here, but we still need 1 over n, right? Okay, so again, the three famous results. For the harmonic series, it diverges. For the alternating harmonic, the sum is log of 2, and for the sum of the reciprocals of the squares of the integers, we get pi squared over 6. I'll collapse these three results and put them in the top right corner. Now let's revisit some terminology from calculus. I'll jump to 3 here. A series is called absolutely convergent if the series of absolute values is convergent. In other words, notice that the series that we were initially talking about is the sum of an, the terms an. And corresponding to that series, there is another series where we just take an absolute value of each of these terms an, and we sum them up. So notice that absolutely convergent refers to the original series. We will say that the series here that we've written in 1 is absolutely convergent if this condition holds, if the sum of the absolute values of n is convergent. And finally, we're now ready for the second case. If we have a series such that this is convergent but not absolutely convergent, in other words, the sum of the absolute values of n is not convergent, then such a series is called conditionally convergent. So going back to the definition of the expected value briefly, you see that the expected value is defined only if the series is absolutely convergent. Right? That's right there in the definition. Now, let's take a look at why we're doing that. As always, let's start by showing that if we were to sum the PMF here over the support, that we'd get 1, that it's a legitimate probability distribution. The PMF expressed in terms of n is 6 over pi squared times n squared, and n goes from 1 to infinity. Okay, so what is the sum? We can pull 6 and pi squared in front of the summation sign, and then what we have left is the sum of 1 over n squared. And we are in luck because we know what this sum is. And so let's bring in that value, and you see that we have 6 over pi squared times pi squared over 6, and we get 1. So it's a legitimate PMF. Okay, now let's take a look at the expected value. What is the expected value of this random variable? Well, as always, it's the sum of the values it takes on times the PMF evaluated at those values, and as x goes over its support. Okay, but now let's express them in terms of n, and the PMF in terms of n is that 6 over pi squared times n squared as n goes from 1 to infinity. Okay, let's see, we have a couple constants here, so let's pull 6 over pi squared in front of the summation sign, and then there'll be a cancellation here in n with the power with n squared in the denominator, and so then what we have left is the sum as n goes from 1 to infinity of minus 1 to the power n plus 1 times 1 over n, right? And we are once more in luck because we know what that is. And therefore what we get for the expected value is 6 over pi squared times the log of 2. So this is some value, right? It's a finite value. We can figure out exactly how much this is, but the point is that it is finite. Now what about the expected value of the absolute value of x? Let me just move this up here to make more room. So I'll move this equal sign there. Okay, now let's take a look at the expected value of the absolute value of x. And what does that equal? Well, it'll be the sum of x over its support of the absolute value of x times the probability of that lowercase x. We'll cover LOTUS in a little bit, and then you'll see exactly why this is the case. But now let's just substitute the values in terms of n, and there's some work here that we can do kind of in our minds without even writing it, because it'll be very similar to what we had here, right? It's just that now we're going to put absolute values in front of this minus 1 to the power of n plus 1 times n, right? So the absolute value will take care of that minus 1 to the power because it'll make it positive. And n is positive already, so the absolute value of that entire business is going to be just n. And then we'll still have the same cancellations as before, and so what we're going to get is 6 over pi squared times the sum of 1 over n as n goes from 1 to infinity. And notice what we have now. Well, it's the third result that's been waiting for us to use it. And it's the sum of the harmonic series, and it diverges. So the expected value of the absolute value of x is infinity. Okay, so what we have found here is a random variable x with a distribution such that this random variable doesn't have an expected value. It does not have an expected value, despite the fact that the calculation of the expected value gave us a finite value. But its expected value is not defined because the expected value of the absolute value of x diverges. Now, why would we do that? We have a series here that is conditionally convergent. It is not absolutely convergent, but who said we need absolute convergence? Why? What does it bring to the table? Okay, we're now about to enter some strange territory. Notice that when we add 2 plus 5 plus 8, we get 15, right? We're pretty confident about that. And if we were to change the order in which we add these values, well, again, we're pretty confident that we're going to get the same sum. Remarkably, this is not the case with infinite series that are conditionally convergent. This situation, where rearrangements do not change the sum, holds only for series that are absolutely convergent. Let's see that in more detail. Let's revisit our good friend, the alternating series. So recall that the alternating series adds up terms that are of the form 1 over n, but the signs alternate. Okay, so this is what we have, and I do want to write quite a few terms here. And we know that this sum equals log of 2, right, from this result up here. Okay, now suppose that we, for some curious reason, wanted to multiply both sides by 1/2. So let's do that. Now I would like to line up these two series, and to do that I'm just going to add zeros. So let's just add a 0 in the first position, and then our 1/2 will go in the second position. Let's add a 0 in the third position, and then minus 1/4 will go in the fourth position, and so on and so forth. Adding zeros is an innocent kind of business where the sum will not change. So the sum is still 1/2 log of 2. And now suppose that we wanted to add these equations 1 and 2 term by term. Let's see what we get. So in this equation 3, we will get 1 from adding this 0 and this 1, and then we'll get a 0 from adding these two terms. Then we get 1 over 3. Then when we add these two terms, we get minus 2 over 4, which is minus 1/2. Then plus 1 over 5. Notice something really interesting here. This is starting to look like the alternating harmonic series. We have the 1 here, we have minus 1/2, we have plus 1/3, but now we need minus 1 over 4. So where's our minus 1 over 4? We're waiting for it. Here we're going to get 0. On the next one we get 1 over 7, and here's our minus 1 over 4. When we add minus 1/8 to itself, we get minus 2 over 8, which is minus 1 over 4. And so we got that term. Then we have 1 over 5. Now we're waiting for minus 1 over 6. And sure enough, we will get that when we'll add minus 1 over 12 2 times. So this is now a very curious thing, because notice what it's telling us. When we add these two series, on the right side we should have, because the top one was log of 2, and the bottom one was 1/2 of log of 2. Okay, but on the left side is just the alternating harmonic series. In other words, 1 and 3 on the left side are exactly the same series. It's just that they've been rearranged. The terms are written in different orders. And look at this strange thing. On the right side, they actually are equal to different values. This is precisely the problem that we're trying to avoid when we require the expected value to be absolutely convergent and not just conditionally convergent. This series that we've been working with here is conditionally convergent, and therefore rearrangements of this series can change the value that we get for it. In other words, if we went with this PMF here and we calculated the expected value of this random variable, that expected value will depend on the order in which we're computing the summation in that weighted average part of the expected value. That would be a very strange thing, and it doesn't match any probabilistic reality. Furthermore, there's a theorem proved by Riemann saying that we could get the sum of a conditionally convergent series to equal any value, any real number we pick. There is a rearrangement of that series which will give us that value. It's a very strange world, and for us in the probability space, that would not be acceptable. So this is why we define the expected value by requiring that the series converges absolutely. So that for a given random variable with a given probability distribution, if we're going to say that it has an expected value, it has one and only one expected value, no matter the order in which the terms are added, right? It's even funny that we're talking about the fact that the order matters. And it does when we're working with infinite series. But the good news is that when a series is absolutely convergent, then rearrangements of the series will not change its value. And that is why we require, in the definition of the expected value, that the series converge absolutely. Let's briefly recap this example because there was a lot going on here. So we looked at a random variable x that has a perfectly legitimate PMF that sums to 1 over its support. When we evaluated the expected value of x, we got a finite value, 6 over pi squared times log of 2. But when we evaluated the expected value of the absolute value of x, we got infinity. In other words, this expectation diverged, because the definition of the expected value of x requires that the expected value of the absolute value of x converges or is finite. We will say in this case that x does not have an expected value. And then we looked a little deeper into why. Why would we not take 6 over pi squared times log of 2 as a legitimate expected value for this random variable? And that has to do with the fact that when we evaluate this expression, expected value of x, we get a series. And this series is only conditionally convergent. And for conditionally convergent series, the order in which the terms are added matters. And when we switch that order, when we arrange the terms, we can get a different value for this series. In other words, for this expected value of x expression, currently we got 6 over pi squared times log of 2, but if we wrote the terms in a different order, we could get a different value. In fact, there's a theorem saying that we can get any real number as the value. There is a rearrangement that will get us that. It's a curious but strange world which we are not interested in, because in probability, this business of the order of the terms mattering doesn't make sense. And that is why we require that the expected value of x be an absolutely convergent series. Because for absolutely convergent series, the order in which the terms are added does not matter. Okay, next let's take a look at the Cauchy family of distributions. The Cauchy family of distributions is parametrized by sigma and theta, and we'll look at one particular member of this family of distributions, the standard Cauchy, which sets those parameters to 0 for theta and 1 for sigma. And then we end up with this slightly simpler PDF for the standard Cauchy. Okay, let's start by making sure that this is a legitimate PDF by checking whether it integrates to 1 over its support. So the support of the standard Cauchy is negative infinity to infinity, and its PDF is 1 over pi times 1 plus x squared, and we can pull the constant in front of the integral, and then what we have inside is 1 over 1 plus x squared dx. And this is a standard integral that we recall is just arctan of x evaluated from negative infinity to infinity. If you've forgotten how arctan works, here's a brief reminder. I plotted tangent of x here. Notice that it has vertical asymptotes at minus pi over 2, but then also every pi distance apart from these. And one thing certain, that tangent of x is not a one-to-one function, right? Because it fails the horizontal line test. So then it doesn't have an inverse on the entire real line. But when we're talking about the arctan, we are restricting ourselves to just the interval on the real line between negative pi over 2 and pi over 2. So now within just this interval, if we had to evaluate for what value of x do we get negative infinity, it's minus pi over 2, right? Over here. And for what value of x do we get positive infinity, it is pi over 2. We get it over there. Okay, so let's evaluate this. So essentially what we have is 1 over pi times arc tangent of infinity minus arc tangent of negative infinity, and that's 1 over pi times, so arctangent of infinity we just saw is pi over 2 minus arctangent of negative infinity is minus pi over 2, and what we will have here is pi over 2 plus pi over 2, which is pi. So we have 1 over pi times pi, and that's 1. So it does integrate to 1. We got ourselves a valid PDF in the standard Cauchy. Okay, well, no surprise there. Okay, then let's try to compute the expected value of the standard Cauchy random variable. So the expected value of this random variable will be, as always, we'll have to take the integral over its support, which is from negative infinity to infinity, of lowercase x times the PDF, which is 1 over pi times 1 plus x squared dx. It may be tempting at this point to make a substitution such as 1 plus x squared equals u. And there's a lot of good reason to think this way, because if we took the derivative of both sides, we'd get 2x dx equals du, and notice that this x dx, that's what we have in the numerator, so that looks very promising. However, this mapping of 1 plus x squared to u is not 1 to 1. So notice for the limits of integration in terms of u, as x goes to negative infinity, u goes to infinity, positive infinity. And then as x goes to positive infinity, u again goes to positive infinity. So it wouldn't work right away, but we see a lot of promise here, and the only thing we need to do before we make this substitution is to split this integral into two. The integral from negative infinity to 0 and from 0 to infinity. So let's do just that. Let me do one more thing here. Let me pull the pi in front of the integral. Okay, and I'll do the same for this other one because it's a constant, and why not? Remembering that the derivative of the log of x is 1 over x, and then the chain rule. So this first term here, this first integral, will evaluate to 1/2 times log of 1 plus x squared. And let's put its limits of integration, negative infinity to 0. And the second one will be the same, 1/2 times log of 1 plus x squared, but different limits of integration, 0 to infinity. Let's quickly check that we got this right. The derivative of the log of 1 plus x squared will be 1 over 1 plus x squared. But then by the chain rule, we still need to take the derivative of 1 plus x squared, and that will give us 2x, right? And then when we'll multiply that by 1/2, the 2's will cancel, and we end up with just x over 1 plus x squared. Okay, so that looks right. And now we are ready to just evaluate this, and we need to be careful here. So what is it that we get? 1 over pi. Then when we evaluate this first expression for x equaling 0, we'll have log of 1 here, which will be 0. And then when we evaluate x at negative infinity, notice that we have x squared here, so we'll get positive infinity. In fact, we'll get log of positive infinity, which will be positive infinity, but we have that minus sign in front. Okay, and I need another parenthesis here. We've got a plus here, and now when we evaluate the second expression at infinity, we're going to get infinity, and when we evaluate at 0, we're going to get 0. So essentially what we get is infinity minus infinity, which is undefined. So we say that the expected value of x diverges. Because the expected value of x diverges, that's it. That's enough for us to say that this random variable x does not have an expected value. But couldn't it be that the expected value of the absolute value of x converges even though e of x here diverged? No, because if e of absolute value of x was convergent, that automatically implies that the expected value of x is convergent. And since we found the expected value of x to be divergent, expected value of absolute value of x cannot possibly be convergent. Okay, so the Cauchy is a random variable that is different than the one we just looked at. In evaluating the expected value of the Cauchy, we get an integral that is not conditionally convergent. We get an integral that is altogether divergent. And once more, that is sufficient for us to say that its expected value does not exist. But unlike in the previous example, here we didn't have to additionally check on the expected value of the absolute value of x. Notice that we have skipped example G, but I think we have enough here. We've looked at an example of a discrete random variable and a continuous random variable in this row 3. And as a reminder, in row 3 we looked at random variables that take on both positive and negative values. And for such random variables that take on both positive and negative values, we have to be careful, because establishing that the expected value of x is finite alone is not sufficient. We still have to go and check that the expected value of the absolute value of x is also finite. Okay, so that wraps up this introductory kind of section on the expected value. Now we're ready to move on to the material that Casella and Berger covered in this section 2.2. Here's the plan for the remainder of this video. There are 4 things that we want to do. First, we'll introduce LOTUS, or the law of the unconscious statistician. In the book, it's introduced in definition 2.2.1. Then we'll move to theorem 2.2.5, which will be about the linearity of the expected value as an operator. And then, most importantly, in 3 and 4, we'll do 2 examples which I think will highlight the importance of LOTUS and the importance of the linearity of the expectation operator. So I want to cover quite lightly 1 and 2 and spend more time on 3 and 4 on the examples. So LOTUS, the name is very suggestive here, right? Because it's got the word unconscious in there, which kind of implies that we may have done something kind of accidentally, unconsciously. So imagine that we have, a random variable y, which is a deterministic function of the random variable x. And now we want to know the expected value of this random variable y. All right, so that's what we're trying to figure out. Well, LOTUS says, okay, well, let's use the definition of the expected value. And let's say our random variable is continuous, so we'll use this top line here. So then the expected value of a random variable by definition is the integral over its support of the values that this random variable takes, okay, which we put here, it's g of lowercase x. But then by definition, what we should have here is not the PDF of x, but the PDF of y, or the PDF of g of x, right? So the word unconscious in LOTUS suggests that we may have accidentally put in the PDF of x there when we should have put the PDF of y, or the PDF of g of x. But it turns out that we're fine. This is correct. And the reason it is correct was covered in great depth in the previous video on section 2.1, because if y is a deterministic function of a random variable x, then x is the only source of randomness for y. So it's no surprise that we can express the probabilistic nature of the random variable y in terms of that of x. So it's no surprise then that we don't need the PDF of y, and we can just use the PDF of x here. And it's the same story if x is discrete. That's about it for LOTUS, but it is very, very, very important. Very important. So we're going to use it again and again and again. This is one thing that you must absolutely understand and use again and again. Theorem 2.2.5 gives us quite a bit, but the most simple and important thing to understand is the following. Suppose that we have random variable y, which is just some constant a plus b, some other constant b, times random variable x. And we want to know the expected value of y. Well, the expectation is a linear operator, so when we write what the random variable y is, we can then apply the expectation to each of these terms. And again, no surprise, because we can do this kind of breaking up of a sum into terms with integrals and with summations, right? So no big surprise here, plus the expected value of b times x, and in fact the constant can come out in front of the expectation, just as a constant can come out of an integral or in front of a sum. And the expected value of a constant is just the constant itself. So we get a plus b times the expected value of x. So this is the simplest and an important example to understand. Theorem 225 gives us different flavors of the same kind of phenomenon. So let's jump to the examples 3 and 4 because they will illustrate exactly why these results are important. Okay, in this example we have that x has an exponential 1 distribution and we form a new random variable y as 3x, and we want to know the expected value of this new random variable y. And we're going to do it in 3 different ways. And I want to start by outlining these 3 different methods. In the first method, we're just going to use the definition of expectation, which says the expected value of a random variable y will be just the integral of lowercase y, or the values that this random variable takes, times the PDF of y dy. And this integral is to be taken over the support of the random variable y, therefore all lowercase y in the support of y. Notice one thing. The fact that x has an exponential 1 distribution means we know its PDF. Right? Exponential 1 is a particular member of the exponential lambda family of distributions with lambda equal to 1. So when we replace lambda with 1 in the PDF of the family of the exponential distributions, we get the PDF of the exponential 1 as e to the power of minus x. And the support of this distribution is between 0 and positive infinity. Okay, so we know the PDF of x, that's given, but we do not know the PDF of y. So in order for us to use this definition of the expected value directly on y, we would need to derive the PDF of y, and we would need to figure out the support of y. Okay, two things that we'll need to work out there before we can use that formula. In the second method, we're going to use LOTUS. And the brilliance of LOTUS is that it takes advantage of the fact that y is a deterministic function of x, and therefore x is the only source of randomness for y, so it is not crazy that we would be able to express the randomness of y in terms of the PDF of x, and LOTUS gives us the exact way in which we can do that. So LOTUS says that the expected value of y, which we'll write as a function of x, expected value of 3x, is just the integral of this function of interest, 3x, times now the PDF of x. That's the key. We put here the PDF of x, not the PDF of 3x, or which would be the PDF of y, right? And because we can use the PDF of x directly, and let me finish writing this. So this will be taken over the support of x, therefore all lowercase x in the support of x. Because we can use the PDF of x here, notice that we do not need to derive the PDF of y. So that's the brilliance of LOTUS, taking advantage of the fact that y is a deterministic function of x, and this gives us a much more direct way to get to the answer here. All we're interested in is the expected value of y, so why go through the trouble of deriving its PDF when we can use LOTUS and use the PDF of x that we already know. Okay. And in the third method, we'll take advantage of the fact that y isn't just any deterministic function of x, but it is a linear function of x. And we'll use the linearity of expectations, which says that the expected value of y, which is just 3x, because this is a linear function of the random variable x, we can write this as 3 times the expected value of x. This is using theorem 225 that we just looked at. And so Now we just need to know the expected value of x. And since x has the exponential 1 distribution, we know its PDF, we could work out its expected value, and in fact we already did earlier in this video. So the expected value of an exponential 1 distribution is just 1. Therefore, the answer here is immediate. It's 3 times 1, and that's 3. But notice that this method 3 applies only when y is a linear function of x. So if we replaced this function here, 3x, with a nonlinear function, let's say minus log of x, now we cannot use the linearity of expectations anymore. Methods 1 and 2 are still in play. 1 is still going too far, and LOTUS will give us exactly what we need in that case. Okay, so these are the 3 ways. Now let's work these out in some detail. Okay, in method 1, we'll need to derive the PDF of y, and we derived the formula for the PDF of a function that is of a deterministic function of another random variable in the last section. So let's use that. PDF of y evaluated lowercase y is the PDF of x evaluated at g inverse of y. So what is this g? So we are saying that if y is a function in g of random variable x, that g is that function. So in this case, g of x is equal to 3x. And we can find g inverse of y. We will in a minute. Let's finish writing the formula. So it's PDF of x evaluated at g inverse of y times the absolute value of d dy, or the derivative of g inverse of y. Okay, so we are given g of x, so this is essentially y. Y equals 3x, and now we just need to solve this for x in terms of y. So x would be equal to y over 3, and this is our function g inverse of y. Okay, and now the derivative d dy of g inverse of y is just the derivative of y over 3, and that's 1/3. Okay, and we've derived everything that we'll need to know to plug into this formula. So then let's evaluate the PDF of y. It will be the PDF of x evaluated at g inverse of y, which is just y over 3, times the absolute value of the derivative of g inverse of y, which is just 1/3. We don't need the absolute value sign, so that's just 1/3. Now let's replace the value of the PDF of x. So we get e to the power of minus y over 3 times 1/3. Okay, we have the PDF of y. Now let us evaluate the expected value of y. Expected value of y, by definition, would be the integral of lowercase y times the PDF of y, and evaluated over the support of y, all lowercase y, and the support of y. Okay, so let's replace PDF of y with its expression, which is e to the power of minus y over 3 times 1/3 dy. And now we need to figure out the support of y. As x goes from 0 to infinity, 3x, which is y, also goes from 0 to infinity, so the limits of integration are 0 to infinity. Okay, now this seems to call for integration by parts. Recall the integration by parts formula. It says that integral of u dv equals uv minus integral of v du. And we'll let y equal u here, and that means that dy will equal du, and then we'll let whatever is left, e to the power of minus y over 3 times 1/3 dy equal dv. So that means that v will be given by the integral of the left side, which is just minus e to the power minus y over 3. Okay, so then let's continue evaluating this expression here. So again, this is our u, this is our dv. So by the formula now, we'll have that equal to uv minus integral v du. So uv, it will be given by y times minus e to the power minus y over 3 from 0 to infinity, and then minus integral of v, which is minus e to the power minus y over 3, and we need du, which is dy. This goes from 0 to infinity. And now let's see what we get. So this first one here is very straightforward, because as y goes to infinity, e to the power minus y over 3 will go to 0. So we'll get a 0 for that. And minus, when y takes on the value 0, so when y is 0, this whole expression will be 0. Okay. Minus now the second one. Notice we got minus, a minus in front here and a minus inside the integral, which will give us a plus. So I'll just write it as a plus. The integral from 0 to infinity of e to the power minus y over 3 dy, and that's just minus 3 times e to the power minus y over 3, evaluate from 0 to infinity. And as y goes to infinity, e to the power minus y over 3 goes to 0, and then we have minus. As y goes to 0, this expression here goes to 1, and we have a minus 3 in front, and then we get that the expected value of y is 3. Okay, again, this was the long way because we had to derive the PDF of y when we weren't asked to do that. We're just asked to derive the expected value of y. And LOTUS gives us a much more direct way of doing that. So let's use method 2 now, LOTUS. Okay, with LOTUS, we have a much more direct way of getting to the answer. Expected value of y is expected value of 3x, and LOTUS tells us that'll be given by the integral of this function, 3x, times the PDF of x, not the PDF of y, or the PDF of 3x. Okay, and this will go over the support of x, which is nice because we do not need to derive the support of y like we did in the previous method. Okay, and let's just replace the PDF of x here with its value, e to the power minus x. And then what is the support of x? From 0 to infinity. Okay, this seems to call for integration by parts again. Put the formula here once more. Integral of u dv equals uv minus integral of v du. And we'll let x be u. That means that dx will be du. And we'll let 3 times e to the power minus x dx equal dv. Therefore, v will be given by the integral of the left side, which will be 3 times, we need a minus e to the power minus x. Okay, so we can continue evaluating our expected value now. So what is uv? uv will be given by x times 3 times minus e to the power minus x. and this is evaluated from 0 to infinity, minus integral 3 times minus e to the power minus x, and du is just dx, and this integral goes from 0 to infinity. And then this first expression now is starting to look familiar, right? When x goes to infinity, this term here will go to 0, and when x takes on the value 0, the first term will be 0. So in either case, we get 0 minus 0 there. And then in the second one, we'll have the integral, and let's see, so we'll have a plus sign because we have two minuses, and then we'll have a 3 integral of e to the power of minus x as we go from 0 to infinity, and that will give us minus 3 times e to the power of minus x evaluated from 0 to infinity, and as x goes to infinity, this goes to 0, so we get a 0 minus, and as x takes on the value 0, e to the power of minus x will be 1, and we'll get a minus 3 in front, so we get 0 minus minus 3, and we get 3 once more. Same answer as we got with the previous method, and that's to be expected. But notice with LOTUS, we have a much more direct way of getting what we want. We're interested in the expected value of y only. We don't need to know its distribution in this case, and LOTUS gives us a direct way of getting that. And method 3 we already covered. It's very simple, but it only applies when y is a linear function of x, which it is in this case. And then, so the more general case is expected value of y when it's a linear function of x. So let's say that y is equal to a plus bx, where a and b are constants and x is a random variable. Then that will be given by a plus b times expected value of x. So in our case, this will be given by 3 times expected value of x, and the expected value of a random variable with the exponential 1 distribution is just 1, so it's 3 times 1, we get 3. So this is the most direct method, but it only applies when y is a linear function of x. Okay, and let's do one more example. In this example 4, x is the uniform 0, 1 distribution, and the random variable y is minus log of x, and we're interested in the expected value of y. And we want to solve it with the same 3 ways, the same 3 methods. But notice right away that y is not a linear function of x, therefore the third method we just used, which exploits the linearity of expectations, is not applicable here. So we have only methods 1 and 2 left. Method 1, in which we're going to have to derive the PDF of y, and method 2, in which we can use LOTUS. Okay, so in method 1, we need to start by finding the PDF of y. So what is the PDF of y? It's the PDF of x evaluated at g inverse of y times the absolute value of d dy of g inverse of y. Okay, so what is g of x here? G of x is minus log of x. So this is y. Y is equal to g of x is equal to minus log of x. And now we just want to solve it in terms of x. So let's multiply by minus 1 both sides. Get that log of x is equal to minus y. And let's think about the definition of log of x. What is log of x? It's the power to which e must be raised so that we get x. Therefore, if we raise e to this power, which is minus y, we should get x. Okay, so this is then effectively our g inverse of y. Okay, so we got that. And then we'll also need to know what the derivative of it is. So what is d dy of g inverse y it'll be the derivative of e to the power of minus y, which is minus e to the power of minus y. Okay, so let's evaluate the PDF of y. It'll be the PDF of x evaluated at g inverse of y, which is e to the power of minus y, times the absolute value of d dy of g inverse of y, which is minus e to the power of minus y. And the PDF of x is just 1, so evaluated anywhere will always be 1, and we'll have e to the power of minus y. So essentially it's just e to the power of minus y. Okay, we have the PDF of y, so now we can find the expected value of y by definition as the integral of y times the PDF of y over the support of y, and we need a dy. Okay, so what does that give us? Let's replace the value of the PDF of y here, e to the power of minus y. And what is the support of y? As x ranges in between 0 and 1, what is the range of minus log of x? So this takes a minute. Let's see. When x is 1, minus log of x will be 0. This is x of 1. And when x is 0, minus log of x will go towards infinity. Okay, so then the support of y will go from 0 to infinity. Okay, so as x goes from 0 to 1, the support of y travels from infinity to 0. We'll need to use integration by parts once more. We'll let y equal u, which means that dy will be du, and we'll let e to the power of minus y dy equal dv. That means that v will be the integral of the left side, which is just minus e to the power of minus y. Okay, and now we can continue evaluating our expected value. So the first term will be uv, which is y times minus e to the power of minus y, minus, and we should put the limits of integration from 0 to infinity, minus integral of v du. V is minus e to the power of minus y, and du is just dy. So we go from 0 to infinity. And what does that give us? This first expression is again familiar. When y goes to infinity, e to the power minus y will go to 0. So the second term goes to 0. And then when y takes on the value 0, the first term is 0. So that first term is 0 minus 0. We don't need to write it. And the second one is effectively the integral. The two minuses give us a plus from 0 to infinity of e to the power of minus y dy. I'll just make some more room here. And that is minus e to the power of minus y, evaluated from 0 to infinity. And when y goes to infinity, e to the power of minus y goes to 0. Now we have a minus. When y is 0, e to the power of minus y will be 1. And we have another negative sign there, so minus 1. And that will give us 1 as the answer. So the expected value of y here is 1. Notice that, again, in this method, we went the long way. We derived the PDF of y, although nobody asked us to. We were just asked for the expected value of y. LOTUS gives us a way to get the expected value of y without having to derive its PDF. So let's look at that next. Okay, so with the second method, with LOTUS, we can get expected value of y much more directly. What is the expected value of y? Well, y is minus log of x. Therefore, now by LOTUS, this will be given by the integral of the function, which is minus log of x, times the PDF of x. That's the key. The PDF of x dx. And we go with the support of x, which is from 0 to 1. And Now the PDF of x is just 1, right? So this is just 1. And so what we really have here is minus the integral from 0 to 1 of log of x dx. Once more, this calls for integration by parts. Log of x is u, then du will be given by 1 over x dx, and dx will be our dv, therefore x will be v. And we can continue our evaluation here. We have a minus in front of the integral, and now we need uv, which is log of x times x, evaluated from 0 to 1, minus integral of v du. V is just x, and du is 1 over x dx, and the integral goes from 0 to 1. Okay, so that's what we have. Let's write this one more time. Minus log of x times x, evaluated from 0 to 1, and then we have a plus the integral of just 1, right? The integral of 1, which is just x evaluated from 0 to 1. And now we can do the substitutions. So in this first expression, when x is 1, log of x is 0. So we'll get a 0 there. And then the minus, when x is 0, the second term here will be 0. So it's 0 minus 0. Plus, for this second term now, when x is 1, we get 1. And when x is 0, we get 0. And this all evaluates to 1. We got the same answer as we did with the previous method, which is to be expected, but more importantly, this was a more direct way to get to the answer. That's it for this section 2.2 on expectations. I hope you enjoyed it, and I will see you in the next video.